what would happen if we include the mass of the photon in the Lagrangian? The Lagrangian for the field we wrote as 1 by 16 pi and Fik, okay. And then we had another term to this, and that was 1 by C, A, L, J, L. Okay. So the second term takes care of the sources. The first term is only for the free fields. Then, if the photon is massless, that means the rest mass of the photon is 0, then it is sufficient. But if you include the mass of the photon to this, then there will be an additional term appearing in this Lagrangian. And that additional term will be given as mu square upon 8 pi, and it should be a scalar overall. So you will have here AM and AM. Okay, so what I was telling you is that you can have the mass of the photon included in this term, and this mu takes care of the mass. Mu is a quantity which is inverse of the Compton wavelength of the photon. Now, what is the Compton wavelength of the photon? It is h cut by mc. So you can write it as m. Mu can be written as mc by h cut. Okay. Now, what is this m? This m is the mass of the photon. Okay. Therefore, this is a very nice expression which can be tested with respect to the observations, and one can confirm whether the photon has some kind of rest mass like the neutrinos, or it has just zero mass, right? Now, what happens when the carrier of the field has some mass, or if it does not have a mass? Now that influences the range of the force. Okay. Now what does it mean? The range of the force, the electromagnetic forces, are long range forces. They get to become zero only when the range is infinite. Now that is the consequence of the fact that photon has zero rest mass. Then only you will have the force that is a long range force and actually getting down to zero only at infinity. The potential will also get to be zero at infinity, as you can see in the Coulomb expression. But on the other hand, if the mass of the carrier particles, carrier means the particle that carries the influence of the force, if that is massless, if that particle is massless, then of course it is infinitely long range force. But if it has got to have some mass, then the forces cannot propagate to that large distance, and in fact they will become zero over a shorter range, right? So such kind of forces will be a short range forces, unlike the long range forces. Okay? Now to us, the meaning will be that you can say that the potential is not the same, okay, which was in case of the Coulomb. So now you have a different potential. Now what is that different potential? Phi at a given point was earlier given as Q by R. Okay. So this is the Coulomb potential. But once you have included the mass of the photon, then this basically becomes different. So you will have e to the power minus mu times r. That means the potential will fall much faster, right? Because this is the additional term. And because it is the additional term, this will make the potential or the influence of the force falling faster, no, compared to the Coulomb case. So one can ascertain this. This mu has the mass. So if the mass is 0, that means photon is massless. In that case, you can regain the Coulomb expression of Q by R. But if it has some mass, then the Coulomb expression obviously will change, and you will have to consider the entire expression, right, along with this part. So greater the mass, shorter will be the range of the force. Now we can confirm this to our understanding about the field equations. The field equations earlier, you remember, were del I f I k is equal to 4 pi by c jk. Okay, so we all know that these were the original field equations of electrodynamics, but they were true when the photon was massless. Now, if the photon has some mass, then you have to work with a different Lagrangian. You have to add that term to the Lagrangian, and that would actually result in addition of a new mass term in this expression on the left hand side. So here you will have mu square, and as you can write here, a k. I want to write here potential, and then you know, to make the whole equation consistent, that this potential should be ak. So this mu square ak is the new term which has been added to the left hand side. And now these are the field equations with the massive photon, right? Now you also know that our photon is spin 1 particle, and the whole field is described by the field coordinate, that is AK or AI, that is the vector potential, that is a 4 vector. Therefore, we call the electromagnetic field as a vector field. It is a vector spin 1 field. In quantum field theory, we call it spin 1 field. Now, spin 1 because the photon has spin 1. Okay, and it is vector field because it is described by the vector potentials, which are like AK. So because of this, one can call it the vector field and the spin, and this is a very common nomenclature in the entire physics. Okay, so I was telling you that when you have these kind of field equations, alternatively, you can write them in the potential, and again recall what were the equations for the potential. So for the potential, you had del I is equal to 4 pi by c and ji. Okay, sometimes I write k, sometimes I, so please don't mind, because it's just a matter of nomenclature of the indices. The only thing you have to take care of is that the free indices on both sides of the tensor equation must be the same, and you have full liberty of changing them, but not during any particular expression or during an exercise. Right from the beginning, you can make a choice about the free indices. So here you can see that the free indices on both sides are I and I there. Now, this is the case when the photon is massless, but if you put photon again with some mass here, then this will change, and you will write here mu square and AI. Okay. So now you can see the whole equation is consistent, and some people also write it like the first box, remember, is the D'Alembertian, right? So D'Alembertian is the 4 divergence, right? So there you are, you have the right hand side given by 4 pi by C Ji. The left hand side is the D'Alembertian plus mu square, right? And don't forget, this mu is basically coming from the mass of the photon. If the photon is massless, the mu will become 0 and you will revert to your original expressions, the conventional Maxwell classical electrodynamics. Okay, so I was telling you that this D'Alembertian is the 4-dimensional divergence, and this is like del I. So by itself, it is a scalar operator, right? And being a scalar operator, it should remain the same in all the inertial frames. So remember this, and you will again be reminded of this expression while talking about the spin zero fields in quantum field theory, in relativistic quantum mechanics, which you will, I guess, study in your 4th semester or so on. But there you have a scalar field, and the scalar field is for spin zero particle, and then you will write the similar kind of an equation, okay? But in place of this AI, you will have a scalar function. So that will be like mu square and phi, where phi is a scalar field. This equation is called the Klein-Gordon equation. Now, can you hear me? So now you know that this is the scalar field equation, and we will not work with this equation. So please don't worry about it. If you like, you can remove this from my discussion. What is important to us is only the equation in the middle, that is the equation for the electromagnetic fields. Okay. So from here, we go back to revise a few things about our earlier lectures. I was trying to write down the manifestly covariant form. So this is a question often discussed. Write the Lagrangian in manifestly covariant form. Okay. So we will see what we mean by it. This is a tensor expression. So you have to use tensors for vectors in writing down the Lagrangian. And we will discuss the case of the free particle, number 1. Then we will discuss the case of the particle interacting with the field. So first of all, we will go back to the free particle Lagrangian, try to write that Lagrangian in the manifestly covariant form. And we will also try to then go to the interacting Lagrangian and try to again write that in form of the covariant notations. Okay. We have already done most of the things. So I will just confine myself to writing down the covariant form. So case 1 is when you have the free particle, right? And for the free particle, I had already told you that this action is the action is minus mcds, right? And this could be also written in form of LDT. And this LDT, if you compare this expression with L, then I told you that this L for the free, let me write one suffix here, small f, to show that it is a free particle, and this becomes minus mc square upon gamma. Okay. Don't worry, even those who join me late, because this is the thing I had already done in my earlier lectures. L free particle, but for the relativistic case. So this is not a non-relativistic case, where in non-relativistic case you will have the free particle Lagrangian half mv square. But here for the relativistic particle, which is a free particle, minus mc square by gamma. So we will try to write this expression now in manifestly covariant form. How do we do that? And let us again see whether it is a Lorentz scalar or not. So we can confirm whether it is a Lorentz scalar. Now look at M. M is Lorentz scalar, right? Look at C. C is a Lorentz scalar. Look at gamma. Gamma is not a Lorentz scalar. As a result of which, this Lagrangian is not a Lorentz scalar, right? So this Lagrangian is not a Lorentz scalar. This dt also in the expression on the left is not a Lorentz scalar. But overall, this quantity is a Lorentz scalar, and therefore action is a Lorentz scalar. So try to think in these kind of terms. Now m in the expression on the right, m is a Lorentz scalar, c is a Lorentz scalar, and ds is a Lorentz scalar. Okay, so how do we write it now in the manifestly covariant form? So L F I said is equal to minus mc square by gamma, and I write it like mc into c, which can be quickly written using the four vectors. The c, you all remember, is the magnitude of the four velocity of a particle. So the four velocity is ui. So you will write here ui, right? And so you have written now in the manifestly covariant form, right? And using this, you can, if you like, you can go back to your action and write the action is equal to LF dt, right? So I will now advise you to write it in the manifestly covariant form. You can again write the whole action in the manifestly covariant form using this expression, and which becomes this is equal to this whole thing into dt. Okay, so can you complete this now work? A, write the action using all this thing. So LF dt, now in place of LF, you write this whole thing, okay? And then you write here dt, okay? So UI you already know. So if you want to open it out, you can obtain from here that this A is actually minus mc and integration of ds. Okay, you can show from here by using this expression of LF, which I have written in the middle. Okay, by using this expression, you can show that the action is minus mc integration of ds. Okay, so please do this as a small problem. It is just a one-line problem, not a technically difficult one. Yes, it is a Yukawa potential, right? So Yukawa term, and it's very important because that tells us the range of the force is determined by the mass of the particle, the carrier particle. Okay, it's very important in physics. So please do this problem, write it down, write down the action as MCDS, and you can use this form of the Lagrangian for the free particle, which is already covariant. And one more thing, if my internet connection goes off shortly, I will revert to that. Please wait and don't go away. The next thing will be to discuss about the interacting Lagrangian. we already knew about this interacting action, right? And interacting action was written as A interacting. When I say interacting, I mean a charged particle is interacting with the electromagnetic fields. Okay. So I wrote here, you will remember, Q by C and AI and dxi, right? How to extract Lagrangian out of it, because Lagrangian is LDT और ये टर्म में इस टर्म में कहीं dt नहीं दिखाई दे रहा है, तो हम कैसे यहाँ से Lagrangian को निकालेंगे? तो जब भी ऐसी कोई डिफिकल्टी आपके पास में आए तो आप हमेशा dt को ले लीजिए, एक एक्स्ट्रा dt ऐड कर दीजिए यहाँ पे मल्टीप्लाई करने के लिए और डिवाइड बाय दिस dt. Okay. And then the rest of the quantities apart from dt on the right hand side is the Lagrangian, right? अब ये क्या हो गया dt, ये Lagrangian, it has now become the whole thing, that is ये चीज multiplied by minus q by c is the Lagrangian, right? अब ये dt थोड़ा odd लग रहा है यहाँ पर नीचे in the denominator, so you can convert it into d tau, right? और d tau और dt में क्या रिलेशन है ये हम लोग कर चुके हैं पहले, कि दो तरह के टाइम होते हैं, एक तो कोऑर्डिनेट टाइम है और दूसरा प्रॉपर टाइम है. कोऑर्डिनेट टाइम का मतलब जो कोऑर्डिनेट सिस्टम के अनुसार चलता है, और प्रॉपर टाइम जो उस पार्टिकल की अपनी घड़ी के अनुसार चलेगा. तो हमको मालूम है कि there is a connection and the connection is that dt by d tau is gamma, right? तो dt by d tau अगर गामा है तो dt को हम लिख सकते हैं गामा d tau, और तब हम यहाँ पर इसकी जगह पर हम d tau and gamma लिख सकते हैं, ठीक है? तो I use this black part in the expression below, gamma d tau. Now gamma d tau का मतलब है कि अब हम इस dxi by d tau को अलग से पहचान सकते हैं, और ये क्या है? This expression is ui for velocity. यही तो for velocity है, और for velocity क्या होती है? So for velocity is dxi by d tau, और ये गामा यहाँ पर बैठा हुआ है. Therefore अब हम इंटरैक्टिंग Lagrangian को लिख सकते हैं, right? This as L interacting, right? और देखें कि क्या वो कोवेरिएंट फॉर्म में आ गया है या नहीं आया है. Okay, so what is it? It is minus q by c, और आगे क्या बचा? ये गामा नीचे बैठा हुआ है तो गामा को हम यहाँ ले लेते हैं, एंड ai, और ये dxi by d tau को अभी हमने कहा you got here minus q by c भी मिला आपको, right? q by c was there, so गामा भी पता चल गया एक, and then you had ai, एक ai का फैक्टर आया और दूसरा ui का फैक्टर, right? So in this way we have been able to write down the whole term on the right hand side in manifestly covariant form, ठीक है? तो इसी को हम manifestly covariant form कहते हैं कि अगर हम Lagrangian को टेंसर्स को यूज करते हुए लिख सकें तो that is manifestly covariant form. Now manifestly covariant, manifestly शब्द का मतलब है कि देखने में हमको ऐसा लगता है कि ये covariant form है. तो क्या ऐसा नहीं है? देखने में ही क्यों लगता है, क्या वास्तव में नहीं है? AIUI, now look here carefully, this AIUI is a scalar quantity. Yes, it is a scalar quantity. अगर आप केवल इतने टर्म को देखेंगे AIUI तो ये एक लॉरेंज स्केलर है, लेकिन अगर इसके पहले बैठे हुए कोएफिशिएंट को आप देखिए तो क्या वो भी लॉरेंज स्केलर है? minus q by gamma c. Q is Lorentz scalar, c is Lorentz scalar, but what about gamma? Gamma is, remember, the Lorentz factor that is related to the speed of the, or the relative speed of the inertial frame, right? The moving frame, which is v, and which has been associated now with the particle itself. Now, therefore, what you will see is that the speed of the particle is not a Lorentz invariant concept, right? We already knew this while writing about the four velocities, because the ordinary three velocities are not Lorentz invariants. So this gamma itself is not Lorentz invariant, and because of this, we cannot say that this Lagrangian is a Lorentz scalar. Obviously, it is not a Lorentz scalar. So it is a good idea. Also remember कि दूसरी चीज है एल की डायमेंशंस क्या है. एल की डायमेंशन एनर्जी की डायमेंशन है, ठीक है. तो दिस एल हैज द डायमेंशंस ऑफ एनर्जी, और जो लैग्रेंजियन डेंसिटी हम लोग इस सिंबल के साथ में ले रहे हैं फॉर फील्ड्स, ठीक है, क्योंकि फील्ड्स के लिए हमको लैग्रेंजियन डेंसिटी लेनी पड़ती है, क्योंकि फील्ड्स एक कंटिन्यूम में वर्क करती हैं, right? They are infinitely dimensional objects, and therefore इनके इसकी जो डायमेंशन होगी लैग्रेंजियन डेंसिटी की, वो ऑब्वियसली एनर्जी डेंसिटी की डायमेंशन होगी, यानी एनर्जी पर यूनिट वॉल्यूम, राइट. आप चाहें तो मास, लेंथ और टाइम के रेस्पेक्ट में या इनको यूज करते हुए भी इनकी डायमेंशंस को लिख सकते हैं. और तब मेरा क्वेश्चन होगा कि AI की डायमेंशन क्या है. AI मतलब वेक्टर पोटेंशियल. तो वेक्टर पोटेंशियल की डायमेंशंस भी आप ML और T को यूज करते हुए लिखने की कोशिश करिए. Okay. Another important thing about this L and this ornamental L is that in case of particles, you have the functions like position, and for particles you have the coordinates like say QIs, which are the generalized coordinates, and they are functions of time. And you can have Q dot I, which are the generalized velocities. Now everyone knows about it, right? And these are the dynamical variables of the system. Now, when you write the dynamical variables of the system, then you define the action with them. And in action, you write L dt. So this is L dt, and this L is a function of this and this, right? And dt. So in this case, Lagrangian is a function of the functions qi, which is a function of time, and q dot I, which is a generalized velocity, again a function of time. It means this Lagrangian is a function of functions, and therefore it is called functional. In mathematics, functionals have more involved definitions, but for our purpose, it is sufficient to say that L is a functional, and this is defined in the space because L is a value, it is a number, it is a numerical number, right? So for every function Qi, you will have a numerical number, and these numerical numbers will be like some number, let's say here 1, 2, 4, 90, 100, okay, and then 95, 2000, okay, whatever. Now these numbers are the values of the Lagrangian, and these numbers are in a space because each of these numbers depends on what kind of function you had. Q is a function of time. So each unique function of the generalized coordinate with respect to time will give rise to a unique value of the Lagrangian, right? So when you define these values in this space, so it is basically the space of functions. So you can say the Lagrangian L is the value of this dynamical variable in the space of functions. And that is why L is called functional. Okay. In case of the fields, as someone had asked me previously, because fields are not discrete systems, then you can have some quantities, let's say phi, which are the functions of position and time. So you can write them as the functions of positions and time. So at each point, you can go and ask the question, what is the value of phi here? 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 So this is actually the meaning of field. What are fields? And therefore, for such kind of quantities, we define the Lagrangian densities. So this was one thing in order, which I wanted to tell you. Also, putting up with the Lagrangian, in a non-relativistic case, you can always write L is equal to kinetic energy minus the potential energy. Now, in non-relativistic case, it is okay. And if someone asks me the question, why this Lagrangian is like this, the difference of kinetic and potential energies, then I will tell you the correct answer comes from quantum mechanics and general relativity. The fact is that all our classical expressions or classical mechanics is just a special case of quantum. Okay, so it is not the other way around. I mean, classical mechanics is a special case of quantum mechanics. It is not that quantum mechanics is a special case of classical mechanics, because you don't go to the classical systems and you don't quantize the classical systems and go to the quantum mechanics. It never happens, right? So first you do the quantum mechanics and then you go over to the classical mechanics as a special case. And then you discover that the Lagrangian is the difference of the kinetic and the potential energy. But that is true for non-relativistic case, and for the relativistic fields, of course, it is not so. And we are already discussing the relativistic electrodynamics. Therefore, in electrodynamics, we don't have this at all. It doesn't work. Even at the earliest step, when the particle, there's charged particle interacting with the electromagnetic fields, we immediately see that this doesn't work. And this is a complicated expression like the energy of the particle, and then minus the interacting part of the energy. So you should write this again, this L, what happens for the interaction, if you include the interaction part for the relativistic case. Okay. Now let's talk a bit about Hamiltonian, because Hamiltonian is again going to play an important role in our future discussions. In Hamiltonian, we wrote for the free particle as gamma mc square. Okay. We also wrote that the conjugate momentum P here was gamma mv, right? So you can also put a vector sign over it with the conjugate momentum, right? And this is defined in phase space in the QP, I mean the generalized coordinate and generalized momentum space. It is not defined in generalized coordinate and generalized velocity space, which is known as configuration space. So Lagrangian is defined in the configuration space, whereas the Hamiltonian is defined in the phase space. So you write this as P and then V minus L, right? So we already did this exercise, but just want to tell you how to write the Hamiltonian, and could it be written in the manifestly covariant form? So if you want, yes, you can certainly play some kind of the same technique, here to write it down in the covariant form. However, writing something in the covariant, manifestly covariant form does not mean that it should be a scalar quantity. So please take that as an important caution, right? So you can again write it like gamma m c if you write, and then ui. So if I ask you to write down the Hamiltonian for the free particle in the covariant form, this is the most you can do. You can't go any further beyond that. And in this, in fact, everything apart from gamma is a scalar. Gamma is not a scalar, and that spoils the whole effect of being called a scalar, and therefore this HF is not a scalar. So remember that this is a scalar, but gamma is not a scalar, therefore it is spoiling the whole effect of calling this Hamiltonian a scalar, and the Hamiltonian obviously is not a Lorentz scalar, right? So this was the case when the particle was free, but if we go to the case of the particle interacting with the fields, then we had already written down this Hamiltonian as, right? I will again try to write down the same expression which I was using with the same symbols. So it is P minus Q by C. It should be rather capital P. Q phi, right? So I'd already told you that in the energy, you don't have the contribution coming from the magnetic fields, but in momentum, you have the contribution coming from the magnetic fields. And this was partly due to the fact that the magnetic forces are velocity dependent forces. And if someone asks me questions as to why the magnetic forces are velocity dependent forces, then I will say because relativity is consistent with the velocity dependence, right? Now, this is a point of discussion, detailed discussion that we can do elsewhere. You can see that this H is, of course, the Hamiltonian, but it is better to call it the total energy. So one can write this as W minus Q phi, and could you square on the two sides? So you will write here m square c to the 4 plus this whole thing. And I will take this on the left hand side. So try to write it down like minus p minus q by c a whole square and c square, divide by c square everywhere. So you will get here c square, and that c square will cancel out here, and you will get m square c square. Now, can you recall this m square c square? What is this? M square c square is actually pi, that is square of the norm of the relativistic momentum of the particle. So you have pi for the particle, a small p. This capital P is the conjugate momentum. Now look carefully. What is happening here is that the relativistic momentum of the particle, I mean the force momentum of the particle, is coming from two different quantities. So one is the quantity like this, right? This and this. So you have a 4 vector on the left hand side as well. And you can break this left hand side into two different things. It is a difference of two 4 vectors, right? So the difference of two 4 vectors by itself is a 4 vector, and you form the square of the norm of that 4 vector, and that you will see is equal to pi. Let's do it quite a bit. We try to break this left hand side into two different 4 vectors. So let's say one 4 vector is pi as a 4 vector, which contains the time component as w by c that is this one in the red below, and the space components as capital P, that is the conjugate momentum, right? And you define another 4 vector which comes as q phi by c, okay, q phi by c, that is one vector, and then q by c a. Okay, there are 2 4 vectors here. Now the difference of those 2 4 vectors is giving rise to the expression on the right. So what we can say here is that the total energy is actually not a scalar quantity. This W is not a scalar quantity, but a time component of a 4 vector. Okay, that 4 vector is Pi. So remember, we can write this as Pi minus Q by C, and the phi and A can be written in a combined manner as AI is equal to, on the right I can write down Pi. Okay, now try to understand this expression, and with the help of the expression down below. Capital Pi is the conjugate momentum, total conjugate momentum containing the contributions coming from the relativistic particle as well as from the fields. So you can add this whole thing here on the right in place of here. This capital Pi is basically a sum of these two. And in this capital Pi, you have P0 on the left hand side, P0 and the remaining components. So this P0 is this one. This is P0 part. P0. This is P0. And the remaining parts of 4 vector are as this. Okay. So everything seems to fit here in these expressions. The total momentum of the total 4 momentum of the field and particles is coming from the particles, that is Pi, and also coming from the fields, that is Q by C AI. Okay. Using this, we also knew that although Hamiltonian can be written in manifestly covariant form, but it does not mean that Hamiltonian itself or the total energy of the system itself is a scalar quantity. It was not a scalar even when the particle was free. It will not be a scalar even when the particle is now interacting with some electromagnetic field. Is the time component of this. So at the most you can say that okay, this is the statement which you can make, that it is the time component of this. So Pi has this time component, that is P0, and the remaining 3 components, which are the conjugate momenta, right? So you can write the same thing on the right hand side as well. On the right hand side, you can think of it like Pi. Now Pi is what? So you can write it as P0 and P, this was the relativistic part of the momentum, plus, now you can write Q by C, and you write here phi, that is the time component, and A. Okay. Or in well-known terms, now you know, you can write it this as I just wrote, W by C, that is the total energy divided by the speed of light. Then this is the conjugate momentum, let it be so. On the right, you have this P naught, which is the energy of the particle divided by C. And this is, of course, the relativistic momentum of the particle. So please add this suffix here, that it is the relativistic momentum of the particle. Okay. And this quantity is the contribution coming from the fields. So I think that you can now save this, and please try to understand that we will have now the emphasis upon this aspect of the Hamiltonian as not being a scalar, but being the time component of some 4 vector. And then we will do further generalization of this, and we will say, okay, the Hamiltonian can be written as time, not just time component, but time component of a bigger tensor of rank 2 while talking about the fields. So that will be the subject of our discussion on Monday at the same time, that is 10:50. If you have any question, you can ask me now. Please go ahead.